Hi there, folks. Today we're looking at similarity in right triangles, okay? And basically what's going to happen here is we're going to start off with a right triangle. We're going to drop an altitude down through this thing, and it's going to give us more right triangles. And the idea here is that all the right triangles it gives us, they're all similar triangles, okay? So the theorem here, the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and each other. And so, once again, the situation is we're essentially going to have three triangles when it's all said and done. The big triangle that we started with, and then when we drop that altitude, it splits the thing into two more triangles. But the idea is that all three of those triangles are going to be similar to one another, all right? And so here's the situation. Here's what it looks like. So here I have triangle ABC, where C is the right angle, so AB is the hypotenuse. And so I've drawn the altitude of the big triangle there of ABC. The altitude is CD, and it's got to specifically be the altitude because that goes from the hypotenuse to that opposite corner. And the reason for that is because the other sides are altitudes if we're to turn this thing, okay? So it's got to be that particular altitude. But what happens is it creates two more triangles. So I had ABC, the original triangle. Now I have two more triangles. I have this medium-sized triangle over here in CBD, and then I have this smaller triangle in terms of ADC. Well, all three of these triangles, the small one, the medium-sized one, and the original ABC, are all similar triangles. All right. The thing that's tricky here is when we first drop this altitude, these triangles are not oriented the same way. Okay, they're not turned the same way. When you look at where the right angle is for each, they're not facing the same way. And so as I start to think about these things and split them off, I'm going to rotate them. Okay, so here is triangle right here. This was that medium-sized triangle of BCD. I've transferred it and I've rotated it. So I've kind of spun it around this way to bring the right angle up towards the top, and then I've flipped it around horizontally. So I'm essentially just kind of taking this triangle, I'm rotating it and flipping it around to make it, to place it in the same directional kind of orientation as the original triangle, the ABC. And so what I'm doing is I'm putting the shortest side off to the left and the hypotenuse at the bottom and the right angle at the top. I'm trying to put it in the same position as the original triangle so we can compare these a little bit better. Same thing with the other one. I take that smaller triangle right over here. So I take this small triangle of ACD, and I kind of move it off to the side, but I rotate it and flip it. Okay, and so as I flip this thing and I move it around to make it in the same directional orientation as the original, now I can see where these different pieces line up. Okay, the piece that's always easiest to align is the right angles. So like for the biggest triangle, the right angle is at C, and for the medium-sized triangle, the right angle is at D. So those have to match in terms of our naming of these similar triangles. Okay. Likewise, the right angle is at D for the smallest triangle as well. And so if I write a similarity statement for these, if I start with the original triangle ABC, I'm going to say that it's similar to triangle. And so when I look at like the smallest one, or let's do the medium-sized one next, I guess, ABC would be the same as CBD. And that's similar to triangle. This one would be ACD. And that's really easy to do once I've rotated these and moved them the same way. All right. The other option here is kind of think of it this way. When I look at like the original compared to the medium size, start with this. Say, hey, C has to be in the same place as D because the right angles have to match up. So here's C and here's D. The other one that's usually easy to match then is the one that they actually have in common, the overlapping piece. Like when you look at angle B in this one, right here, well, that's the same as angle B in both triangles, in the big triangle and the medium-sized triangle. So here's B, matches up with B. And then C and A are kind of the only thing that we have left to match up, okay? Same thing with the smaller triangle. Again, match up the right angle first. When you look at the biggest triangle, the right angle is C. And when you look at the smallest triangle, the right angle is D. And now the angle that they share, well, is angle A. That's an overlapping part. So A has to be in the same spot. And then the only thing left are B and C matching up. Okay, so again, lots of ways to think about this, but it's really important to understand the similarity and make sure you have these listed appropriately, because we want to start comparing the sides of these similar triangles, and we can't do that if we don't know which sides correspond. Okay, so it's really important to make sure we understand the similarity statements here, and if that takes kind of moving the thing and rotating it to draw it in the same manner as the original, go for it. If that means matching up some individual angles, go for it, okay? We have to make sure that we have the similarity statement right, all right? For example, if I look at something like this guy, it says, find the lengths of the missing sides. And so once again, if you're looking at this going, this is really hard for me to see, split it up, okay? Let's kind of rewrite this thing and kind of orient them the same way. And so when I look at the big triangle has the hypotenuse off to the right, and then it's got the right angle off to the left. And so if I take this medium-sized triangle right here, ABD, well, let's turn it the same way. It would look kind of like this. I'd put the right angle over here, the long side there, the short side here, and the hypotenuse over here. That was a terrible drawing. I can do better than that. I didn't quite draw it large enough. Okay, and so what happens is I start to move this thing around. It looks like D is this guy right here, A would be this guy right here, and B would be this guy up here, all right? And so again, I'm just turning it the same way as the original. And again, look at the right angle for the original triangle is at A, the right angle for the medium-sized one is at D, okay? The hypotenuse is BA for the smaller triangle, it's BC for the original. And then label these pieces. You know, this guy was a 5 inches, and this guy was a 13 inches. Okay? And then take the smaller triangle, the very smallest triangle, and do the same thing. So once again, I've got these different pieces here. Let me orient it the same way. If this is the right angle. For the smallest triangle, the hypotenuse is AC. That's this guy right here. And the right angles at D. So now these are all facing the same way, okay? And really, it just makes them easy to compare. And so as I kind of look at this thing, I can just kind of ignore everything that's inside here now. I can just look at that triangle as a whole. The only other thing that I need here is AD. Over here, this was the 5 inches, okay? And so as I start to compare these things, now I can see, you know, the hypotenuse of each is right here. And yeah, I don't know the hypotenuse of this one, so I'll call it X. I also don't know the hypotenuse of the biggest triangle, so maybe I'll call it something like Y. Okay, that's for this whole thing. And then as I start to compare some of these other sides, like the smallest side on the medium-sized triangle, this guy, well, that would compare to this side right here, DC. Well, I don't know what that is, so maybe I'll call it something like Z. Okay. And as I look at this, AC over here on this last one, I don't have that with, that's the hypotenuse of this guy. This is also X over here, okay? So just making sure that I label everything in the same way, AC and AC. So kind of understanding those corresponding, those matching, those overlapping pieces. And now from here, we might want to try setting up proportions. The problem is that in order to set up a proportion here, everything that's in the same position, I'm going to have too many variables, okay? And so there's a couple options here. One of them is to try to go the route of using a variable that's the same, using that X twice. But that doesn't quite work out for this one because I don't have enough information. The key here is this first triangle that I have drawn off to the side. I can actually find the missing side of that one without the other triangles, without using proportions. This is a right triangle where I can use my Pythagorean theorem, okay? And so if you use the Pythagorean theorem on this one, I'll call this A over here, just A squared plus B squared equals C squared. And I can actually solve this one. And I find out that A equals a 12. So now I have this missing side as a 12. And that will allow me to use proportions to find everything else. So ignore the big triangle off to the side. Let's just do the small triangle here. I could say that, hey, the 12 goes to the 5 the same way that the 13 goes to the x. Because these are similar triangles, I can cross multiply and solve this thing. And this is not going to work out nicely, but that's okay. We can just divide that on our calculators here. I'm just going to round it off. I'm going to say this is a 5.42, something like that. And then I could do the same thing to find the other missing side. I would say, hey, you know what? The 12 goes to the 5 using that same proportion, the same way that the 5 goes to the z this time. Okay? And once again, I can cross multiply. And I'll just plug this one into the calculator again. I'm just going to round it off. So z equals a 2.08. And now I can expand out and look at the biggest triangle over here. I can do the same thing. I can say that, hey, 12 goes to 13 this time. The same way that something like 5 goes to x. And now I could cross multiply, although I already have x, and if I cross multiply and solve this, I'm going to get the same thing. Forgot we already have that one, right? That's going to be our 5.42. So let's do the y. So let's see, 12 goes to 13 the same way that 13 goes to y. And I cross multiply. And I solve. Got to divide each side by the 12. And I get approximately a 14.08. Okay? And so as I look at these, I've got every missing piece of this thing. I got the 14.08 over here. I have the z, which was the 2.08, and then I have the 5.42 here. So I have all the little pieces of this thing. I have every piece of this triangle, every missing value in terms of the missing lengths. Okay? But again, it all started with making sure I could see clearly which pieces matched up from each triangle. Okay? So writing those proportionality statements and putting these triangles in a way that I can see which sides match up. Okay? For this one, it says find the length of the altitude. And so for this particular example, I'm going to split these guys up, but I don't need to find all the sides. So I want to really pinpoint exactly what I want to find, and that's this guy. Okay, so I'm going to label it right now so that I know I want to find x. I want to find that altitude. Okay, and so as I look at this thing, if I start to split this thing up, all right, so maybe I take the small triangle off to the side here. And I'm going to turn it this way, so it's just a little bit easier for me to draw. So I put the 3 centimeters over here and the x down here. And so when I look at this thing, this is D, this is A, and this is C. So I've kind of just turned it on its side, put the longest side on the bottom. And I've turned it in the same way that I already have the medium-sized triangle. So let me draw that. Let me draw it a little bit bigger so that you can tell it's the medium-sized one. And that was 10 centimeters here. That was x over here. And that's DCB. And then if I want to redraw the big triangle off to the side over here, I can. Okay, but the big triangle, if I did this would be CB. This would be AC off to the side over here. And really, the only thing I have is the hypotenuse actually at 13. Okay? And so as I look at this thing, if I only want to find x, well, the biggest triangle doesn't really help me because it doesn't involve x at all, okay? So if I start using the big triangle, I'm not going to find anything that I want to find, all right? So I want to look at these two triangles, and it seems like I don't have enough information at first, but keep in mind, that's the same variable in both of these. So it's still going to be one variable. If I were to kind of set up the proportion here, it's 3 over x, comparing the smaller sides, equals x over 10, comparing the larger sides. Well, it's still one variable. Yeah, I'm going to end up with x squared here as I cross multiply. So here I cross multiply, I get x squared equals 30. But that's okay. I just have to take the square root to solve this thing. So I take the square root of each side. And again, this will be a job for my calculator. I'm just going to round this. Well, actually, you know what? We could keep this one in radical form. It would just be x equals the square root of 30. And there's no perfect squares to divide evenly in there, so I can leave that the way it is. Or, if the question calls for it, it kind of depends on the situation, we might want to write this as 5.48 if I round it to 2 decimal places. And for this particular example, it might be better to have this in terms of a decimal because we're talking about centimeters. All right. But in another example, it might be beneficial to leave it in radical form because we want the exact value. And maybe we need that to predict other values or find other values. Okay. And so this leads us to kind of a shortcut here. So when we look at this thing, if I break these triangles up the same way every time, here's the shortcut. The thing we call this is a geometric mean. So geometric means are when the means of a proportion are the same. And remember extremes and means when we write our proportion this way, A to B. The next proportion would then be like B to C. Okay? This is an example of where we have a geometric mean because the means, the values in here, are the same. And we kind of saw this in fraction form a moment ago. If I were to write this as a fraction, this would be A over B equals B over C. And so when we're talking about geometric means, an easy way to think about geometric means is when we set the diagonals of the proportion equal to one another. So right here, when B is the geometric mean, they just go across from each other in the proportion. And we saw that right here in the previous example with the x. Okay? In that previous example, x was the geometric mean for that proportion. It was the geometric mean between the 3 and the 10. And so this leads us to this corollary that we're about to state. Essentially, we're just going to say what we just discovered, and that's that x right here, the altitude, is the geometric mean between these two pieces. Okay? And so that's what this says. It says, hey, the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. And so when I look at this, this is going to work every time. Instead of having to split up the triangles, I can take a shortcut. I just say that, hey, this guy is the geometric mean between these two pieces. And when I set that up, the geometric mean, I just set those across from each other in my proportion. And then the other two values are the other two values. That's what it means to be the geometric mean, okay? It means the means are the same. Well, from the perspective of setting up a proportion, it just means we set that value across from itself. Okay? We can extend this out a little bit, and as we kind of split the triangles up and find other values that would end up being geometric means of one another, or finding geometric means with other values, we get this other corollary. And this one's a little bit more confusing. When we look at the words, it almost doesn't make sense to us. When we look at the proportions that are written, it almost doesn't make sense. But when we look at the picture, it'll make a lot more sense. Okay? So the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of the leg is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. And if that all just sounded like gibberish to you, hang on for a second. Let's look at the picture here. So like when I look at this one, right here, x is the geometric mean of the piece that it's closest to and the whole hypotenuse. Okay, and that's all this is saying. So here, x is the geometric mean, piece that it's closest to, and the whole hypotenuse. Okay? I do the same thing with y. If I look at y is the geometric mean, that's why it's across from itself, of the piece it's closest to, and the whole hypotenuse. And that's it. It's just a shortcut, and we will arrive at the same thing if we split these up and looked at the right triangles, looked at the similar triangles. We would get this same thing because of the overlapping pieces. Okay? But this is a shortcut that we can go right to setting up the proportion without having to split these up, okay? And many students really struggle with splitting these up and seeing which pieces actually correspond, okay? But that's our fallback. If we can't remember this thing, we can split these up and do similar triangles the same way we did on the previous page, okay? But again, x, the altitude, is the geometric mean between the two pieces. When I look at each leg, the leg is the geometric mean between the piece that it's closest to and the whole hypotenuse. Okay? Likewise, the other leg is the geometric mean between the piece that it's closest to and the whole hypotenuse. Okay? And again, that sounds complicated, but in context, this is much easier when we start doing examples. Okay? For example, if I look at this guy, it says find x, y, and z. So let's start with x. X is the geometric mean. That's the altitude. So x is the geometric mean between the pieces of the hypotenuse. So here, x is the geometric mean, so I set x across from itself. And it's the geometric mean of the pieces of the hypotenuse. Well, that's the 12 and the 4. So I just plug in the 12 and the 4. And it doesn't matter the position I put these in, because remember, proportions, I can switch the diagonals. And now I cross multiply and solve. Here we go. This is an x squared equals 48. I take the square root of each side. And again, I'm going to leave this in radical form this time. That's 48 is 16 times 3, so that's a 4 root 3. Remember, square root of 16 is a 4, the 3 is still trapped. The next one, I'm going to do that one in radical form also, but now when I look at the legs, this is the one that's a little bit tricky. So if I looked at y, so y is the geometric mean, so I set it across from itself, of the piece that it's closest to. So now I'm looking at that hypotenuse. The piece that the y is closest to is the 4. And the whole hypotenuse is 16. So it's the geometric mean between the piece that it's closest to and the whole hypotenuse. And now I cross multiply and solve. Here we go. Cross multiply, that's a y squared equals 64. I take the square root of each side, and I get y equals an 8. That one worked out nicely. And now I do the same thing with z. Z is the geometric mean, so I set z across from itself. Okay, they're the diagonals. And it's the geometric mean, just like y, it's the geometric mean between the piece that it's closest to and the whole hypotenuse. It just is a little different because z is closer to the 12, so the piece that it's closest to, and the whole hypotenuse, which is 16. And now I cross multiply. So let's see, that's going to be z squared. The 12 times the 16, that's going to be a 192. And now I look for perfect squares that divide evenly into this one. I believe that's divisible by a 64. Yeah, it's going to be divisible by a 64. So let's see, that's going to be an 8 root 3, it looks like. Okay? And again, that's because 192 is 64 times 3. The square root of 64 is an 8. The 3 is still trapped. Okay? Again, these are all centimeters. And here's the thing. Once again, if I wanted to, I could plug these into the calculator, get a decimal approximation pretty easily. It depends on the context, though. Sometimes we'll want the decimal. Sometimes we'll want the exact value, which is leaving these in terms of square roots. Okay? If I look at this one, it's kind of a basic example of just find the geometric mean between these two values. So again, just going back to that idea that the geometric mean is when the thing is across from itself. So I don't know what the geometric mean is, so I'll call it x. So x is the geometric mean between 4 and 9. I just fill in the other two values, okay? And this is just devoid of any context. You know, in the case of the right triangles, we have context for the geometric mean. But now I cross multiply. X squared equals the 36. I take the square root of each side, and technically when I take the square root, and we've been ignoring this because we've been talking about measurements, technically the square root is plus or minus 6, okay? But for our purposes in geometry, typically we're only worried about that positive value because we can't have negative side lengths, okay? So for now, I'm just going to say the 6, okay? But don't forget about that algebraic aspect. That'll be important when you get back to pre-calc, okay?